All right, thank you, Crystal, and thank you to the organizers for having me here today and for putting on this great conference. I've been really enjoying the variety of talks this week. So yes, I am going to continue today's theme of learning about stellar astrophysics in the early universe by observing things in the very nearby universe. And I should clarify, since I'm following these stellar archaeology talks, metal-poor stars in my world are basically metal-rich to people like Keith and Alex. In the massive stars community, the stars I'm talking about are, considered extremely metal-poor because they're below 10% solar metallicity in some cases. So different regime, but very relevant for early universe physics. So, okay. I am interested in O-type stars. These are the stars that are massive and hot enough to produce ionizing radiation. And these are also the stars that at low metallicity are providing, feedback and dominating the UV and ionizing radiation from galaxies in the early universe and in dwarf galaxies across cosmic time. Now, JWST is routinely finding that galaxies at high redshift in the reionization era need to have metallicities of something like 5 to 10% solar. And so we need to have good models of stellar evolution and spectra in this low metallicity regime if we want to accurately interpret observations of these galaxies. Now, the stellar population synthesis codes that we use to do that necessarily adopt stellar evolution and spectral models that must make some assumptions about key stellar properties, okay? And since we're not all massive stars people in this room, I'm going to take a few minutes and just step through a few of these key properties that are expected to be metallicity dependent and have the largest impact on these model predictions. So first, these massive stars produce a lot of energetic radiation that transfers momentum to the outer layers of the stellar atmospheres. This is through interaction with metal transitions, okay? So this figure is showing the dependence of mass loss rate on the stellar luminosity at a fixed metallicity of 20% solar. And the key point here is that these two different model predictions are very, very different. And so theoretically, we do not have a great handle on the physics of stellar mass loss at these very low metallicities. And it's important to get the mass loss rates right because mass loss affects stellar evolutionary pathways and end products, and also sets the hardness of stellar ionizing spectra. Okay, so these weaker winds that are expected at low metallicity are also thought to be less efficient at removing angular momentum from stellar surfaces. So evolution models predict that more metal-poor stars are able to maintain higher rotation rates throughout their main sequence lifetimes. And this fast rotation induces additional mixing, which increases surface temperatures and lengthens stellar lifetimes and overall boosts ionizing photon production relative to non-rotating stellar models. Okay, and then third, we get into the thorny issue of binarity, okay? We know that this is common in massive stars, and we know that interactions between binary stars can boost ionizing radiation from a stellar population versus, single star models that don't account for this. And it's especially important at ages much older than single O-star lifetimes. But this opens up just a whole can of worms, right? There are a lot of free parameters that go into this, and it is really not known what, if any, metallicity dependence in this kind of interaction and ionizing radiation exists. So, okay, to get a handle on how to parameterize all of these things in stellar evolution and spectral models, we actually need spectra of individual massive stars to constrain the distributions of these properties. But below the 20% solar metallicity of the small Magellanic Cloud, which is about 60 kiloparsecs away from us, spectra of individual O-stars are very rare because to find such low metallicity O-stars that are still around means that we have to look to star-forming galaxies that are all the way at the edge of the local group. So we really do not have empirical constraints on these various aspects of stellar physics that really do matter for our SPS models that we have to use to interpret observations of galaxies in the early universe. So this is the gap that I am working to fill with new observations, and I'm sure that we will hear about some complementary work in this direction from Peter in the next talk. But my talk is going to focus on a sample of 3 O-stars in nearby dwarf galaxies that span 3 to 14% solar metallicity in terms of their gas phase oxygen abundances. And okay, these seem like ridiculously close to a lot of people in this room, I think. We're talking between 1 and 1.6 megaparsecs away. But to the stellar community, this is incredibly far. It's more than 25 times the distance to the SMC. And people had basically written this off for quite a long time as something that you could not do. But you can, actually. So our team has used the Hubble Space Telescope's COS instrument to observe far ultraviolet spectra of these 3 stars. And these spectra encode just a whole bunch of different information about the physical state of the stars' photospheres. But for this talk, I am going to focus on just a couple of features in these really rich data, 2 pairs of wind-sensitive lines that give us diagnostics of the stellar terminal velocities and mass loss rates. Okay, so zooming in on these lines, basically COS has showed that these metal-poor stars have very weak stellar wind profiles, okay? We do not see well-developed P Cygni profiles. We see blue-shifted absorption, but there's no really prominent red emission peak like you see in many stellar models. This is telling us empirically that these are very weak winds, but to actually quantify that statement, we need more observations. Of course, that's always the answer, right? We cannot actually break degeneracies between the mass loss rate and other stellar properties from the far UV spectra alone. It turns out that you need optical spectroscopy as well. So in a new paper I just put on the archive about a month ago, we present new KCWI observations of these 3 dwarf galaxies. KCWI is a really blue-sensitive integral field unit spectrograph on the 10-meter Keck telescope, and really we need that big glass in order to get decent signal-to-noise spectra at high enough resolution to do the measurements that we need. So these 3 images are showing white light, 16 by 20 arcsecond fields in these 3 dwarf galaxies, and you see that we are resolving individual stars, right? And so the 3 targets are in these blue circles here, and in each pixel of these white light images, we have a full spectrum from 4,000 to 5,000 angstroms. And the extracted spectra of the 3 target stars here show really nice detections of important stellar absorption lines that give us diagnostics of 2 really important stellar parameters. We have the surface gravity, which comes from the broadness of the Balmer absorption wings, and we have the effective temperature from the relative strengths of helium-1 and helium-2 lines in these spectra. And this is the important diagnostic for O stars. If you get into later type, B stars, and there are different lines that you need, but for O stars, it's really all about the helium. Okay, so with these new spectra in hand, we then did a quantitative analysis of the joint optical and UV data sets. So I ran a whole bunch of new stellar atmosphere models using the power code and iteratively adjusted many different parameters in these very difficult to run models. They take days to converge sometimes, but eventually we got a model for all 3 stars that can reproduce the full suite of UV and optical diagnostics that we observe. And so from these best fit models, we can infer the properties of the stars and their winds. And so for the first time, we can now finally compare quantitatively the mass loss rates of these stars to expectations of these different theoretical treatments of stellar winds. So this figure is showing the mass loss rate, again, as a function of the stellar luminosity. Our measurements for these 3 stars of the colored points with error bars here, where the color indicates the iron abundance adopted in our best fit power models. And for comparison, the colored lines and squares up here show 3 different theoretical models at the same metallicities. And the key takeaway here is that overall, our stars agree best with this more recent modeling by Björklund et al., 2021, which is at the low mass loss rate end of this wide range of model expectations. And this is actually really important to take into account in the context of stellar models, because most evolution codes that produce isochrones that are widely used in SPS codes today adopt this sort of classic Vink et al. 2001 prescription. And again, you can see on this log-scaled plot, this is more than an order of magnitude difference from what we're actually observing. So these low metallicity stars at the low luminosity end of this relationship are really not losing a lot of mass at all. And again, this is not a subtle difference, okay? So to drive this point home, this figure is showing the difference between our best fit model, which is the red line here, and the blue model, which adopts the mass loss rate that's predicted by this Vink et al. Prescription if I plug in all of the inferred properties of the star from our best fit model. So this looks very different, and it's, I think, worth considering in this community, right? Because JWST is really only accessing the rest UV of the highest redshift galaxies. And so we have precious few diagnostics of the stellar properties, and the wind lines really are one of them. So to connect the observed wind features with the properties of the stars producing them, I think is going to require an update to these models. Okay, and how am I doing on time? Oh, okay, great. I want to very briefly conclude by pointing out something unexpected in this analysis. And that is that the properties of the 2 stars below 10% solar metallicity do not agree with the predictions of single star evolution models. So basically, we find surface gravities from those broad Balmer absorption wings that are much higher than expected from the positions of these 2 stars at the ends of the main sequence here. So this could be pointing to missing physics in our evolution models at these low metallicities. An alternative explanation is that they are in binary systems, right? We know that binaries are common in massive stars, but though that seems like a nice, simple explanation, even an equal mass binary system cannot really explain away this tension, because if you have an equal mass binary, these would move down by 0.3 dex in luminosity, and that is still not enough to bring them on to the mid to early main sequence, where they would need to be to have these high surface gravities. So another possibility is that they were in binary systems and interacted in the past in a way that changed their structure. And in a sense, this would hang together with the high rotation speeds that we measure for these stars, but really we've not been able to find an evolutionary scenario that can simultaneously explain everything that we observe about these stars. So they really have posed some new questions for us to tackle, and I will be very interested to see if, this kind of result proves common in larger samples going forward. Okay, so to wrap up, I'm just going to leave you with a summary of my talk and end by advertising a new observing program that is really going to expand this analysis to a much larger data set, actually boosting it by a factor of 10 in terms of number of O stars that we can analyze. So the Treasury of Extremely Metal Poor O stars, or TEMPOs, is a Cycle 31 Hubble Space Telescope program. It is getting new COS and DEIMOS spectra of these 29 stars, and together we will be able to scale up this analysis to stars spread across different environments in galaxies between 5 and 10% solar metallicity. And this is really designed to be the best possible sampling of O-star parameter space that we can do given current technological capabilities and our current census of confirmed O-stars in these nearby dwarf galaxies. Okay, and then finally, just a quick advertisement for those of you in the room who are interested in this bringing together of low metallicity massive stars and high redshift science. Found out just about a week ago that we have a new Aspen Center for Physics workshop that has been approved for next summer. So keep July in mind and look out for the application deadline at the end of January. All right, thank you. Happy to take questions.
raise your hand for questions, or you can stretch and walk up to one of the microphones.
So thank you, Grace. This was wonderful, and I think it's very, very relevant to all the science that we have been discussing. So my question is, I know I hate to ask you this question, but what is the dependence on the atmospheric models that you are using? Because,
yes.
I mean, we all know that this is a very tricky business.
Yes,
and,
totally.
So I'm wondering, you know, before saying that our current understanding of stellar evolution is actually limited at this metallicity, which probably it's true, maybe, you know, what are the relevant physical parameters that you are sensitive to when you work with these atmospheric models? The atmospheric models, you know, would bias somehow, or could bias somehow your results.
So you're basically asking, are the stellar atmosphere models robust? Yeah, okay. Great question. We should always be skeptical, yes. So yes, I did use a particular code, and I am one person. I had to make choices in the modeling, as we all do. I actually do think it is quite robust, and I have two reasons for saying this. One is that a master's student at Amsterdam is doing a thesis that I'm co-advising that includes these 3 stars. He's using an independent code, completely different. It's fast wind wrapped in a, you know, genetic algorithm routine. So he has a completely different way of estimating uncertainties too, and he's getting results consistent with what I did, including the weird properties of these 2 very low metallicity stars. The other reason I say that is a massive stars collaboration called X Shooting Ulysses recently put out a paper. It's Sander et al. 2024, where they did a sort of comparison challenge where they had maybe 8 or 10 people fit 3 stars in the LMC and SMC independently using their own codes and techniques. And they found reasonably good agreement across at least the fundamental stellar properties, which are what I'm comparing to the evolution models. So, you know, there are systematics, but I think this is pretty robust.
All right, can we have Peter come ahead up, and we'll take one more question.
Okay, so in the actual synthesis models of early universe galaxies, like how big of an effect is this going to have?
Oh, that's such a good question. I would hesitate to venture a guess based on 3 stars, honestly. And so that's part of the motivation for doing the bigger tempos program. That is definitely something we are working toward, but this is, you know, an end of survey kind of result. There's a lot of atmosphere modeling and such that has to go into it beforehand, but yeah, stay tuned. Yeah. Okay. Thank you.